Here's the energetics unit, HL Chem. Yay. It is chapter 5 in your book. Yeah, we're skipping around a little bit. That's all right. Okay, so questions we're going to keep in mind for this chapter or this unit. What is energy? What types of energy are relevant to chemical reactions? What additional definitions can help us identify energy changes in a reaction? And we're going to find that number 3 is kind of crucial in our understanding of energy. Let's get a couple terms down. Thermodynamics is the study of energy and its transformations. And then thermochemistry is the study of those energy changes involving heat during chemical reactions. Okay, energy is. What do you know? Hang on while I get the clip. If we look at this famous video clip of the Hindenburg.
From the ground, you can see the forward control cabin from which the ship is operated. The windows along the side indicate the location of the passengers' quarters, in which many were carried to a flaming death. Approaching Lakehurst, the Hindenburg appeared a conquering giant of the skies, but she proved a puny plaything in the mighty grip of fate. It almost seemed as if fate had set the stage for the horrible tragedy. A graceful craft sailing serenely to her doom. For 3 hours, the dirigible circled the landing field at Lakehurst, New Jersey, dumping more water ballast than ever before in vain efforts to level off. Again she dumps ballast, and a nervous tension grips those who are watching, for this is something unusual. There goes more ballast, but the tail is settling in spite of all that has been dumped. A grim note of impending tragedy. Finally, the landing lines are dropped. These scenes were filmed by Pathé News cameraman William Deek, and you're about to see the pictures he got when the ship exploded. Those aboard leaping for life from a flaming inferno. The actual crash of the Hindenburg. An airship destroyed in less than half a minute.
I think that gives you some idea of the amount of energy that can be contained just from chemical reactions, because that is a combustion reaction. And an awful lot of energy was released in that famous Hindenburg blimp. All right, let's get back to our conversation about energy. Potential energy, hopefully you're familiar, is the energy an object possesses by virtue of its position or its chemical composition. Okay, and really, you know, what does that mean? Well, you know, there's the infamous you drop a book and everybody wakes up in the classroom because I've lulled them to sleep. But more stable systems are ones at lower potential energy. So chemical compounds or atoms and bonds are going to form so that they lower the potential energy of the system. And then kinetic energy, we've talked about it, is the energy an object possesses by virtue of its motion, and that's equal to 1/2 the mass times the velocity squared. And remember, in chemical compounds, some of that kinetic energy is just the movement of the particles. And then there's a different type of energy that I kind of want to point out is the electrostatic potential energy. And this is really related to ionic compounds. It's the energy that arises from the interactions between charged particles. Now, K is just a constant, but Q is the charge typically on the cation. The other Q, capital Q, represents a charge, is the charge on the anion. And then D is the distance between the ions. And that's related to something called the electrostatic energy. This is mainly related to ionic bonds. Hopefully you might have inferred that, being as we're talking about cations and anions. Okay, let's talk about energy. Energy is defined as the ability to do work or transfer heat. Work is the energy used that causes an object that has mass to move. Energy used to cause the temperature of an object to rise or cause a phase change is called heat. So it's kind of like you have the physical motion of moving things that have mass, and then you can also use this energy as a heat energy to put into a system or to take out of a system. The units of energy are the joule. 1 joule is 1 kilogram meter squared over second squared. This is something that you should know. Okay? Know this. Which means memorize that. You should know that a joule is 1 kilogram meter squared over second squared. That's something I have to remember every year, but now that I've seen it again, I'll remember it. Okay. An older non-SI unit still in widespread use is the calorie. I'm sure you've heard of it. 1 calorie is equal to 4.184 joules, and that's considered an exact number. So you shouldn't limit calculations on sig figs based on that conversion. Just some interesting quantities of energy. You can pause if you'd like to look them over. Now let's get back to definitions. And this is a really important definition, is the system versus the surroundings. If we look at this piston system, I have a cylinder and a piston. Probably the area that I'm most interested in is going to be the interior of the cylinder, okay, the molecules and the space that these molecules take up. That's going to be the system. The surroundings are everything else. Here, you could consider them the cylinder and the piston. They also include everything else outside of that space that contains those molecules. We have 3 types of systems. We have an open system, and that can exchange energy and matter with the surroundings. That would be, typical would be a boiling pot of water on the stove without a lid. Closed system can exchange energy with the surroundings. That's going to be that same pot of water, but maybe with a lid on it, so the matter doesn't go off as steam. And then there's an isolated system, and that's where matter and energy are constant within the system, meaning there is no exchange of matter or energy. It's isolated. So 3 systems: open, closed, isolated. So heat. Energy can be transferred as heat. And heat flows from warmer objects to cooler objects. And it has to do with the collisions imparting some of that kinetic energy and transferring that heat. Okay, first law of thermodynamics. Energy is neither created nor destroyed. So energy is conserved in all processes. Okay, an important thing to keep in mind is an energy diagram. Maybe not keep in mind, but to understand. And the idea is that we look at this y-axis as being energy of the system. If a system starts here and this is its initial energy state, E initial, if it ends up at a lower energy state, okay, so energy, we've gone from a higher to a lower, that means energy has to be lost to the surroundings. Energy of the system decreases. This, of course, hopefully you will see as an exothermic change, okay, because that energy is leaving the system. Now, conversely, if it starts at a lower energy, energy is absorbed from the surroundings, moving it to a higher energy. Hopefully you'll recognize this as an endothermic change. I can spell it. Okay. But because of the first law of thermodynamics, total energy of the universe is a constant. If the system loses energy, the surroundings have to gain that energy, and of course, vice versa. If we talk a little bit about the internal energy of a system, the internal energy is the sum of all of the kinetic and potential energies of all of the components of the system, and it's represented with a capital E. Okay, so by definition, your delta E, change in energy, internal energy, is the final energy of the system minus the initial energy. Okay, and this is really what this delta means. Delta is really final minus initial. And we can be talking about internal energy, we can be talking about temperature. Delta, you take the final minus the initial. Okay, so when energy is exchanged between the system and its surroundings, it is exchanged as either heat, represented by a lowercase q, or work, represented by a W. So here's the heat represented by Q and work represented by W. So my internal energy, energy of the system, is really the heat and the work. Now at this point in the screencast, I am going to derive a well, not quite yet. That comes in a little bit. Hang on. So for Q, if Q is positive, it means the system gains heat. If it's negative, it means the system loses heat. Okay, so this is positive for that endothermic change that we've talked about, and minus for the exothermic change. But for work, a positive work means work is done on the system. So work is being put into the system, energy is being put into the system. Negative means work is done by the system, so the system's doing work on the surroundings. So for change in internal energy, if I have a plus, there's a net gain of energy by the system. If I have a minus, there's a net loss of energy by the system. Okay, really, we don't have to worry too much about this concept. We'll come across it in another topic shortly. But if a system gains energy and work is done on that system by the surroundings, the overall delta E, or change in internal energy, has to be endothermic. If energy is released by the system, Q is negative, and work is done by the system, meaning W is negative, then the change in internal energy must also be negative. These middle two cases depends on the sizes of Q and W. Whichever one's larger is going to be the predominant force, making delta E either positive or negative. Okay. So, heat absorbed by the system, process is endothermic. Heat released by the system, it is exothermic. We've seen a couple of examples in class, so I'm going to leave that with the examples we saw in class for endothermic and exothermic. The next couple of slides are really going to be kind of optional, so I think I'm going to make them into another screencast. So this is where I'm going to end this screencast, and we'll pick up either with you watching the optional or picking up at the discussion of enthalpy.